9.2, we're going to continue our discussion of experiments today. What happened in 9.1 was what's called single-step or single-stage experiments. We only did whatever our experiment was one time. So if you rolled the dice, you rolled them one time. If you had a child, you had one child. If you played the game, you played it one time. Whatever it was only happened one time. So what's going to happen today is that we're going to do an experiment where it's repeated. So maybe you roll the die twice. You have the two kids, or you play Uno twice, whatever your thing is you're doing something twice or more, okay? That's the difference. Now that introduces more difficult sort of process in making calculations. So in particular, what we're going to be doing in this section are what's called tree diagrams. So a tree diagram is a sample space model where each outcome is designated by a separate branch. We're not going to do them on every single problem because there's going to be some other strategies we can do. But if we don't do a tree diagram, we're going to be doing something similar to it. Okay? So every single problem is going to have some visual diagramming of what's going on in our problem. So one-stage experiments, those are the ones we did last time. Experiments that are over after one step, i.e. one set of branches. And then a two-stage experiment is an experiment that's over after two steps. And we could obviously, blend this into like a three-step. It needs three sets of branches and so on. The most that you're going to be asked to draw, I believe, have 4 stages, but most of them are 2s and 3s. Okay, most of them are smaller than that. There is a multiplication rule for tree diagrams. So for all multi-stage experiments, the probability of an outcome along any branch of the tree diagram is equal to the product of all the probabilities along the path. So we're going to be doing some multiplying along branches. And here's my note. Highlight it, star it. It's really important. I expect to see tree diagrams or something equivalent on all your work, every single problem, because this is what your students would be doing. Okay? Are there simpler ways to do it without the visual diagrams? Well, of course there are. Right? Mathematicians, we will work with probabilities all the time without a tree diagram. But the underlying sort of like image of what's happening is still a tree diagram. So we're working with the underlying image in this class. So allow yourself space for doing this. I know sometimes when we don't know how to do a problem, we skip some space. You might need to skip more space because there's going to be something going in there that's going to take more than a couple of lines. All right, last time you looked at something called mutually exclusive events. Independent events are slightly different. They sound like they're the same, but they're not. Independent events are events of which one occurrence has no influence on a second occurrence. Right? So if I get pregnant and have a baby, the gender of that baby has absolutely nothing to do if I get pregnant a second time and have another baby. Those are completely independent events. If I toss a coin, we'll toss a coin, and I get heads, that has absolutely no bearing on what happens if I toss the coin a second time. Those are independent events. Right? One has no bearing on the other. But that doesn't always work with everything. Right? Think about a card game. Right? You've dealt all the cards out. The card you draw next is not independent of all the other cards, because some of the cards you can't pick because they're already in other people's hands. Right? That's not an independent draw. It's dependent on the other things that have been drawn. So some events are independent and some are simply not. When you have independent events, sorry, I was right there. When you have independent events, E1 and E2, and you want to know the probability of having both of them happen, you multiply their probabilities together. And that's exactly what's happening and why we're getting this multiplication along tree diagram branches, is that it's representing independent outcomes, so we can multiply them together to see what happens and how we would get both of those things to occur. And we're going to put all of that together in an example now. You ready? Okay. An executive committee consists of 10 members, 4 women and 6 men. 3 members are selected at random to attend a meeting in Hawaii. Do you want to go? I want to be selected. I think we should all raise our hand and say, pick me, right? Yeah, absolutely. Okay, so yes, there's 10 people, but there's not 10 people going. Yes, there's 10 people, but the issue is not about whether or not specifically Sally goes or Joe goes. What we're actually asked to find, if you'll flip the page, is what? The probability of them being a woman or a man. Do you see what I'm saying? So there's only 2 categories of things that can happen. Even though there's 10 different people that can be picked, they're putting them into some kind of categories. So you'll see problems that deal with gender, like this one. You'll see problems that could deal with like classification, right? So are you talking about high school students, junior high students, elementary students, freshman, sophomore, junior, senior, right? Things like that. But something where you can put people in some kind of categories. That's what you're going to see happen on questions like this. So taking a look back at the original problem over here then, it says that we have 2 different options when we select our first person. Oh, that was supposed to be a straight line. Let's try that again. Our options are that when I pull that name out of, think about names in a hat maybe, right? If I pull that name out of the hat, they're either going to be a male or a female. Now, initially, when I make that draw out of the hat, how many men are in there? 6. Out of how many total slips of paper? 10. So there is a 6 out of 10 chance that when I select that one, it's a man's name, right? All right, what about the women? 4 out of 10. Okay, and if I were simply drawing one person to go to Hawaii, this would be over. It'd be a single stage experiment. And we'd kind of be like, I didn't need to draw a picture for that, right? Which is why you didn't see that going on in the last section. We didn't really need one for that. But we're going to do a second draw. So the second draw actually draws a set of branches off of the first set. So a few things that will help you in drawing these. Draw them long. The longer you draw your lines over, right, the more space you're giving yourself to write things out, because the more spread apart they are. You can also draw yours sort of from a top-down perspective. So if you'd rather draw them sort of like this, and then branch off like that after that, down here, you could do it that way. I tend to draw mine left to right. Okay, the same options exist, male, female, as we had before. But what's different in this one, and we'll see diagrams where this isn't different, but it's different in this one, is that these are not independent events. I don't still have 4 men's names in the basket. Or 6 men names in the baskets. I don't still have 4 women's names in the basket, right? I already picked one out. So because I picked one out, all my probabilities are going to change on the next go-round. So if I'm going along the top branch, I've picked a man's name out, which means how many men's names are still in there? There's only 5. So it's 5 out of how many slips of paper are still in there? 9. What about the women? Is it?
Oh.
It's still 4, because on the top branch, the woman's name didn't get picked. So I still have a 4 on that one. It's not 4 out of 10 anymore, it's 4 out of 9, but it is still 4. Are you guys following okay? Okay, great. Next one. If I'm on the bottom branch, though, I have selected a woman's name. So how many men's names are still in the basket? The same 6 I had originally, but there's only still 9 strips of paper. How about women's names? There's 3. Okay, everybody good? Seeing where all those numbers are coming from? It's important. Okay, good. That would be what I would do, and I would stop if I only had 2 people that were going to Hawaii, but I have 3. So I do the branches one more time. Notice they get to be a lot of branches. And they're all labeled, much like they were before, with the males, females. And each branch has to be considered based on what's been done in the past. So the very top one, where I am up here, up here, has the reality that there was a man's name drawn on the first draw and there was a man's name drawn on the second draw, right? So in that case, how many men's names are still in the basket? 4. How many names total? 8. How many women's names? Still 4. How many total? 8. Now, on the next set of branches, though, they first drew a man's name, and then we second drew a woman's name. So one of each has been selected along that branch. So how many men's names are still in the basket? 5. And it's still out of 8. There's only 8 left in all of these cases. How many women's names? 3 out of 8. Okay, bottom set of branches. Now on this one, I drew a woman's name first and a man's name second. Okay, how many men's names are left? 5 out of 8. And women's names? 3 out of 8. And you might be saying, well, didn't we just do that? And the answer is yes. Right? The order that I drew the men's and the women's names in didn't really matter. The result was still the same. I still have the same number of men and women left in these 2 middle branches. Again, this is unique to our problem here, but that's happening for a reason. Okay? My bottom branch, 2 women's names have been drawn. So how many men are still left in that basket? 6 out of the 8. And women? 2 out of 8. So this is considered a complete tree diagram. We put all the possibilities in here. We put all the probabilities on each of the branches. Okay, this is a complete tree diagram. It's a triple stage, right? 3-stage one. So if you flip over to the next page, though, we're going to answer some questions. Typically, the questions themselves are not the difficult part. The difficult part's drawing the diagram. Okay, we're using the diagram now to answer the questions. So the first question said, what is the probability that all 3 selected are women? So where do you see that happening on this diagram? The very bottom one, right? Okay, it's down here. And what we heard in a previous slide is that to get the probability of along that branch, I simply multiply the individual probabilities that happened. Okay? So we're going to be multiplying those individual probabilities, which is 4/10, 3/9, and 2/8. Now, you are welcome to multiply across the top, multiply across the bottom, and reduce things. That's okay. You're also welcome to reduce and not do that multiplication. So if you notice, for example, that 3/9 is just cancel the 3's, I get 1/3, then do it. 2/8, same thing, it's 1/4. 4/10, that would be 2/5. Even if all you did was that significantly reduced the values I have to multiply. We'll just stop there for my reducing and see what happens. So now if I multiply across the top, I have 2 times 1 times 1. It's 2. And across the bottom, I have 5 times 3 times 4. 60, very good. This isn't in simplest form, because what else can I still reduce? Yeah, I can divide it by 2 on top and bottom, right? And I would get 1/30. Now, 1/30 is a very small probability, right? If you were to put it in your calculator, you'd get something about like 3% approximately. It's very small. It's not very likely to happen. But that should make sense because there's fewer women's names in there for that to be even possible, right? And there's other combinations where we select people that include both genders instead of just one anyway. Okay, the other one says the probability that at least one man is selected. So the probability of at least one man. So I'd like for us to take a look at the locations where we see at least one man on this diagram. Where do you see those? Sorry, say again, Faith.
The one that starts with the male.
Okay, obviously everything that starts with the male. So it would be this one, and this one, and this one, and this one, right? Okay, what else? Good observation. Say that louder for me.
Well, the one that we just worked with were all females. That means all the rest of them have at least one male. So it would be all of them except the one that we just got.
Okay, you're exactly right, Kaylee. So this one has the male here, here, And I have one here. The only one that's not in this description is the green one at the bottom. So there's two ways to do this problem. Option number one is that we can multiply along every red branch, which would mean we'd have 7 sets of multiplication, and then we could add those 7 sets of multiplication all together. Or we could do 1 minus the probability of having all female, which we happen to have already calculated. But even if we hadn't already calculated it, we'd only need to calculate one branch, right? So if we even had to go back to the part A and do that all over again because that wasn't the original question, we would have ended up getting that this is 1 over 30. And we would do 1 minus 1 over 30. So what is 1 minus 1 over 30? Don't overthink it. 29 over 30. Right? It's all the other ones. They have to add up to 1. 29 over 30. Were we overthinking it? Maybe, yeah, a little bit. It's okay. It's 29 over 30. It is very, very likely that at least one man's going on this trip. Now, the reality is it's very likely that at least one woman's going on the trip too. If we were asked the same question, but we flipped the question to say how many, what's the probability that it's at least one woman's going on the trip, we'd have all the branches at the bottom 7 highlighted, and the one at the top that we would be subtracting off is the one that's along the top. It'd be slightly bigger, right? A slightly bigger number to subtract off, but we'd still end up with the majority of our groupings of 3 people, including both a male and a female. Okay, you good? All right. So this next one is actually one where we can do it with a slightly different sort of structure that doesn't include a tree diagram. It's equivalent, but it's just going to look different, okay? So we've got a box that contains 5 slips of paper, numbered 4, 6, 7, 8, and 9. A player reaches into the box and draws out 2 slips of paper, and he adds them up. Okay, can you picture what he's doing? Okay. If the sum's even, he wins. If it's odd, he loses. So what I'd like for us to do is simply to write down all the different 2 slips of paper that could be drawn out. But we want to do this in an organized way so we don't duplicate anything and so that we don't miss anything. So I'm going to start with the number 4. And I can't do a 4 and a 4 because there's only one slip of paper with a 4 in it. So I could pick a 4 and a 6. Or I could pick a 4 and a 7. Or I could pick a 4 and a 8. Or I could pick a 4 and a 9. So let me make this a little bit taller here. Here we go. These are the only options for having a 4. I've written down everything that has 4s in it, so I stopped writing 4s down because I've written them all. So we're going to move on to picking a 6. Okay, again, I don't do 6 and 4. I already wrote that down. So I could do 6 and 7, or 6 and 8, or 6 and 9. And you notice there's one fewer because I'm missing the 4, 6, right? But I don't need to write any more 6s down. I've included all of them. So I could include 7 with some things. I already did 7 and 4. I already did 7 and 6, so I don't need to write them again. What else could I do with 7? 7 with 8, and 7 with 9. What am I missing? I'm missing 8 and 9. That's the only other thing that I haven't written down at this point. Everybody good with that? So what I'm doing here is I'm writing down all of these different options. The reason I can do that here and I couldn't do that on the last problem is because they're all equally likely, right? There's not 3 4s in there. There's 1 4 and 1 6 and 1 7 and 1 8 and 1 9. They're all uniquely different. Even if I had 5 men and 5 women, I couldn't have done it this way on the last problem because I have 5 women, right? Not 1 woman. That's why I can do this on this problem. Now, what I'd like to do, I'm going to spread mine out just a little bit because we're going to do something with them in a minute, is I'd like for us to think about which ones of these end up being even. Now, you're welcome to actually add them together, or you're welcome to sort of eyeball it and say, yep, I know this one's even. Yep, I know this one's even. So we're just going to go down the list and decide together, do I have an even result or do I not? And I'm going to highlight them in red. 4 and 6, is it even? Yes. 4 and 7? No. 4 and 8? 4 and 9? Okay, everybody good so far? 6 and 7? No. 6 and 8? 6 and 9? No. 7 and 8? 7 and 9? 8 and 9. Okay. So I've highlighted the ones that are red. The evens are the ones when they win. So how many options actually let me win this game? 4. But how many options are there? We didn't count before. There were 10. Now, anytime we end up with a probability in fraction form here, we're going to make it in reduced form. All right, just like we did back in chapter 6. Okay, that's not going to be any different. 4 and 10 will reduce to what? 2/5. So we have a 2/5 probability of winning. This now says, does it change if the numbers are multiplied? In other words, the rules are the same. If I win if I'm even, I lose if I'm odd, right? But I'm going to multiply the values instead. So instead of red, I'm going to change it and we're going to do a blue. Okay, so our question is, if I multiply, do I get an even? 4 times 6. Yes. 4 times 7. 4 times 8. 4 times 9. Why are all those going to be even automatically? They're all multiplied by 4, and 4 is even. So what does that tell you about the column with 6's in them? They're all even as well, because I'm multiplying by an even value. What about the 7, 8, 7, 9, and 8, 9? Any of those even? 7, 8 is, and 8, 9 is, because they're at least one even, right? So how many ways do I win if I multiply? 9. Out of how many? 10. So we answered the question by finding the value. Does the probability change if the two numbers are multiplied? Yes, it does. And it changes to 9/10. Okay, so not all random games are truly random, right? Now, there's other numbers that I could have had given to me that would have made this a little bit less lopsided. Right, notice I have more even numbers in the basket than I have odd. So we're working in favor of multiplying to an even here. Yeah, so. Okay, here's another one. These are spinners. Suppose an experiment consists of spinning the first spinner, right? Think of board games as spinners, followed by spinning the second spinner. Now, these are drawn on purpose to be evenly distributed, right? So it's a 50-50 shot on the first spinner. It's exactly half and half. The third one's exactly in thirds. So it's not trying to mislead you. That's not the point of the problem, okay? So you can go with your gut on some of those things of what it looks like. The first question says to find the sample space. So you talked about sample space in section 9.1. Sample space is just a list of all outcomes. Well, I don't have the structure drawn on this one. That's what I did when I listed everything out here on the first problem, right? Before I started highlighting anything. That's essentially a sample space. It's not drawn out really very formally looking, but it's the idea of what a sample space is. So we're going to do a sample space, but we're going to do it more formally for this, okay? So we're going to put the S for sample space and an equals. And these are sets, which means they go in curly braces. Okay, so that's the formalizing of what we're doing. And we're going to write ordered pairs. That's how we're going to write it. For example, if I spin the first spinner, I could get a 1, right? And then after I spin the 1, I move on to the second spinner, and I could spin and I could get a second 1. So one option is I get spinners that go with 1 and 1. But again, I'm trying to make an organized listing. I could spin spinner 1 and get a 1, and spin spinner 2 and get a 2. Or I could spin spinner 1 and get a 1, and spin spinner 2 and get a 3. And all of these are equally likely because it's equally likely that I spin a 1 and a 2 on spinner 1, and it's equally likely that I spin a 1 and 2 or 3 on spinner 2. These are equally likely sample space options. So a sample space doesn't have to be equally likely, but this one, ours we're working with right now, it is. All these outcomes are equally likely. All right, the next one. I maybe don't spin the spinner 1 and get a 1. I could spin a 2 on that one and could get then spinner 1 and spinner 2 would give me a 1. Or I could get a 2 and a 2. Or I could get a 2 and a 3. And all of these compiled together in the curly braces is my sample space. Okay? Now, I don't have space on my screen, but in your notes, the next line of questions follows. So we want the probability of each of those things happening. Now, these are all equally likely, which means there's 6 outcomes. So whatever I get is going to be a value over 6, kind of like the last one was whatever I get is a value over 10. There's 10 possible equally likely outcomes. So the one we're looking at right now says spinning 2 even numbers. How many of my spins give me 2 even numbers? Just one of them. This one right here, right? That's the only one that gives me 2 even numbers. So there's 1 out of how many spins? Or some options? 6. Yeah. How about spinning at least 1 2? Yeah, everything that has a 2 in it will now be highlighted. There's 4 of them. Whoops. So we have 4 out of 6, which will reduce to 2/3. How about spinning exactly 1 2? 3. So in this case, this one right here doesn't count anymore because it has 2 2s. But the other 3 that I highlighted in blue do count. So it'd be a 3 out of 6 probability, which is 1/2. Okay, we will do one more and then we'll push pause till next time, okay? We're ending on a fun one. This was written ages ago when my now 15-year-old son was quite little and prone to staining his shirt constantly. When I purchase a new shirt for my son, there is a 0.15 probability that he will stain it the first time he wears it. If the shirt is stained, there's a 0.2 probability that I will not be able to adequately remove the stain, right? It's stained forever. You ever had that happen before? It's annoying, isn't it? Oh, frustrating. What is the probability that my son's new shirt will be permanently stained after the first time he wears it? Okay, so there's 2 different things that are happening. Can you tell me what one of the things is? Does he stain the shirt or not? Okay, this is one of the parts of one part of the experiment. There's either a stain or it's not stained. That's the first part of the experiment. What happens next? You either can get the stain out or you can't. I include this one in here because I want you to see that not all tree diagrams are symmetric. This one, if there's no stain, I don't treat the shirt. I just stick it in the wash and I move it on, right? So I don't have a second set of branches on the no stain one. It goes in the laundry basket. But if it's stained, I have to do something special with it. Now, if it's stained and I scrub it, what are the 2 possible outcomes? It comes out or it doesn't. So I like that phrasing. So the stain comes out or it does not come out. Now, this is not complete. What's missing from my tree diagram? All the probabilities everywhere. So let's fill them in. What is the probability when he wears the shirt the first time he stains it? 0.15. I'm pretty sure there's no way it was that low back in the day, by the way. No way. How about the probability that he doesn't stain it?
0.2.
Nope. Okay, so how did you get 0.85, Kaylee? Oh, Faith. I thought it was Kaylee. Is that Faith? Okay, so this is something I wanted to mention on this one as well. Notice, every tree diagram pairing of branches adds to 1. It's a 100% thing, right? And it happened on the other ones that we did too, over here. If I can find it. These add to 1. And these 2 add to 1. And these 2 add to 1. And it happens every single time. So your branches will always add to 1. And what that means is that if you know one branch, the 0.15, you can find the other one because you can subtract it from 1 to get to the 0.85. Okay, good deal. How about, what's the likelihood that the stain comes out? 0.8. Why is it 0.8? All right, it says the probability that it is not able to be gotten out is 0.2. So the 0.2 is actually my second description here, right? And that means the 0.8 goes on top to add up to the number 1. Okay, does that make sense? That's the tree diagram to support the answer, but we don't have the answer quite yet. We're almost there. The question says, what is the probability my son's new shirt will be permanently stained after the first time he wears it? Well, that means it's got to be stained. And then which branch would I follow next? That does not come out. Which means what do I do to get the result of that diagram's branch? You multiply. 0.15, we multiply along diagram branches. What is 0.15 times 0.2? 0.03. That's a 3% chance, right? 0.03. Okay, and we will push pause right there for today.